Alright guys, we are going to talk about states of matter. I know you usually have a little picture of my face on here, but for some reason my webcam is not working right now, so it's just my voice this time. Alright, so quick review that matter is anything that has mass and takes up space, which is basically everything. Everything has mass and takes up space that you and I can think of. Even the air we breathe, it has a mass and it takes up space. The mass might be very tiny, but it definitely takes up a lot of space. Basically, outside of our atmosphere, where the molecules are so few and far between, that is where you lose, and it is not technically matter anymore. It is empty space, which is why it's called space. So we're going to talk really quickly about the kinetic molecular theory. Kinetic, the word kinetic means movement. So the movement of molecules is essentially what this theory is about. So this explains how particles, atoms or molecules, in matter behave. We know all matter is composed of particles, either atoms or molecules. We know that particles are in constant random motion. Okay, that means that they are moving as much as they can and they bump into each other and they blast off in a new direction. And particles collide with each other and the walls of their container when they are moving in this random motion. So, states of matter. There are 4 states of matter. Now, you guys are all probably very familiar with solids, liquids, and gases. Plasma is a newer one, and there are technically a few more states of matter than what I have here, but really for our purposes, we're only going to learn about these 4. So the first we're going to talk about is a gas. A gas has no definite volume and no definite shape. It also has a low density. So if you look at how they behave, okay, if you have this, okay, molecule right here, or excuse me, this bottle of perfume right here, and obviously there are molecules and atoms in the air around you, and if you spray that perfume and you stand across the room, you're going to eventually smell it, and that's because gases diffuse really easily, because once you spray them into the air, they dissolve into the air or evaporate into the air, and as that happens they randomly move around and hit each other, and as they hit each other they get further away from each other and eventually will travel all the way across the room. So that's basically the behavior of the diffusion of the gas right there. So see, these are all the random movement of all of them, and you can see they're kind of bouncing off each other and they're ending up in all places all across the room. So we'll go ahead and do the next one, which is a liquid. A liquid has a definite volume. That means it fills a very specific amount of space, but does not have a definite shape. Obviously, if I pour water into a bowl and I pour water into a jar, the water is going to take the shape of whatever container it's in. That's why it does not have a definite shape. Okay, it does diffuse fairly easily, but not as easily as gas. So basically, if you spray that perfume like we just saw, you'll notice that it'll very quickly diffuse across the room. Now, the same diffusion happens in water, except let's say I drop a drop of food coloring into the water. It will eventually move and become evenly distributed throughout the water without me even stirring it. But it will not happen nearly as fast as that perfume bottle going through the air. And part of that has to do with how fast the molecules are moving. So liquids are not compressible. That means that you cannot fit a certain amount of volume and squish it down so that it is less. It basically has a specific volume and it has no definite shape, meaning it forms to the shape of whatever container it's in. It also has this very cool little characteristic called surface tension. So we know that a liquid is made of atoms and molecules, and those atoms and molecules will make up the entire amount of that liquid, and they will be attracted to each other on the surface, and this causes something called surface tension. It keeps the surface of the liquid together. And we're going to look at what that implication is in just one second. So here is our random bottle, and notice that when we turn on the liquid, it fills the shape of the bottle. Okay, but if I put it in this bowl, it also fills the shape of the bowl. So it doesn't have a definite shape. But if I push down on that water, it isn't going to become less. Okay, it doesn't compress at all. So you have that, and now if I pour that water onto the table, it's going to make a huge puddle. So it definitely has a definite volume, but not a definite shape. So if we compare it to a gas, so here's the gas molecules. Notice that they're all moving. These guys move past one another. Gases are much further apart than liquids. So just be aware of that. Like if you look at that, the amount of gas molecules, okay, are really far apart, but when I compare them to a liquid, look how close they are together, but they're still able to freely move past one another. So they're a lot closer together, which is why you can't compress them. They can also diffuse. This is what I was talking about, is this is one liquid, this is another liquid, and notice that eventually they'll bump into each other enough and diffuse to be equally distributed throughout the mixture of liquids. And then surface tension. So this is the attraction of those molecules, like I said, across the surface of the water. Okay, and this is basically a huge reason why bugs can walk on water, is this surface tension. All right, so we're going to move on to the next one. Now, solids. Solids have a definite shape, meaning they don't change shape depending on where they are. If I take a block, it is still going to be a block no matter if I put it in a bowl or a cup or on the table. But it does have a specific volume as well. So if it's a 1 by 1 block, it's going to stay a 1 by 1 block, and I cannot make it smaller. I can't push on it and make it any smaller. It does not diffuse easily. Now it does diffuse, which is a little confusing, not exactly what you'd think, but it takes a long time for it to be able to diffuse. Something that we really wouldn't be able to comprehend. It takes that long. And in solids, atoms are tightly packed together in geometric arrangements, and these are technically the most dense of all the states and are incompressible. So we're going to look really quickly at that. So we have our solid here. Okay, and if an elephant stands on it, that elephant is not going to squish that block of wood, that's solid, okay? Well, I mean, I guess it might, so baby elephant. But it basically has a definite volume and a definite shape that cannot be changed. And the molecules are so close together that they can barely move at all. So if you compare this to what the liquids were and what the gases were, where they could flow easily past each other, these guys really aren't moving. All they are doing is they're close together, okay? And they are incompressible. If I push on them from both sides, they are not going to change shape. Okay, and this is what I was talking about with the diffusion. It doesn't really diffuse super. Okay, so back here. So the final state that we're going to talk about is plasma. And plasma is a gas that has gotten so hot and has so much energy in it that negatively charged free electrons, remember electrons can be lost and gained in atoms, so those negatively charged free electrons, they're just floating around, and positively charged ions, these are the atoms that have lost those electrons, so now they're positively charged, are surviving right next door to each other. And so they're able to run electrical charge. They are very, very able to conduct electricity compared to the other states. And it's the most common state of matter in the universe. And we'll talk about why that is in a second, because most of the things in the universe are super, super hot. So think about that. They have, because they are a gas, they have no definite shape and no definite volume, though you may think otherwise when you think of our example. So, a plasma, as we said, is the most common form of matter in the universe. Our sun is an example of a giant ball of plasma. So, if you look back at the sun really quick, okay, basically it looks like it has a definite volume and a definite shape. However, we are losing little bits of plasma into the universe all the time and generating new atoms in the core with the heat. So you are kind of you're not getting that definite shape and definite volume as you would think you would be. So yeah, that's the sun. And most stars are this form of plasma. Anything that's superheated is going to be this form of plasma. So basically all the matter in the universe is either planets or stars, mostly stars, and they are all made of plasma. So that's why the universe is mostly made of plasma. So we do have man-made plasma, and we can do that in different electrical light bulbs. Because they are able to conduct electricity so well, we use them a lot. So we have our electrical light bulbs, our plasma TVs, any neon signs are made of plasma, and we just superheat them so that these electrons leave their atoms, and then all the free electrons and the positively charged ions exist together. All right, so finally, states of matter basically depend on temperature. So a specific state of matter occurs in only one specific range of temperatures. And the temperature of something is related to the average kinetic energy that an object's atoms or molecules have. So if an object's atoms are moving really, really fast, okay, the temperature is going to be very high. If an object's atoms are moving extremely, extremely slow, it's most likely going to be solid. If they're moving medium speed, maybe a liquid. If they're moving and they're superheated and they're moving super fast and they are charged, there will be a plasma. Thermal expansion. So thermal expansion is something that does happen almost always, which is the increase of size of a substance when the temperature increases. So essentially, if you heat something up, it's going to become bigger. The volume is going to increase because the molecules are going to move faster and bounce off of each other more, which is going to fill up more space. The only exception to this rule is that water, when you freeze it, actually expands, so it actually fills more volume when it is cooled than when it is in its liquid form. Okay, so those are the states of matter. I hope that makes sense.